Welcome to today's lecture. We will continue our discussion on the thermal response of aqueous biphase inclusion and the response particularly to heating experiments. And these experiments we are calling as homogenization experiment, because our objective is to obtain or to attain the same homogeneous state from which the inclusion was trapped. To continue our discussion, we were discussing about the liquid vapor homogenization, and there were two cases in which the inclusion would homogenize either as L plus V to L or L plus V to V. And coming into a little bit of practical aspect, we were discussing as to how we are assured that we have actually recorded the temperature of homogenization. There, with forward increase in temperature, we will reach a temperature which is the temperature of homogenization, where the vapor bubble has disappeared, and we have recorded the temperature, and those kind of a situation will give us. So, when it comes to temperature of homogenization, means where we are working in a temperature of the order of more than 200, 250, 300 or even sometimes more than that. So, there if we can reproduce the value to plus minus 1 degrees centigrade, then we say it is fairly acceptable. But sometimes there are problems, like if we have, so that is what if we want to actually assure that whether we have determined the temperature of homogenization or have been accurately recorded the disappearance of vapor. This may happen because the inclusions geometry may be very irregular, which we will be demonstrating to some videos later, that the inclusion geometry might be such that when the vapor bubble is getting reduced to very tiny size, it may just get hidden inside any of the margin, and we may not be able to record the temperature of homogenization by the exact point at which the vapor bubble disappeared. So, the best practice here is that where we have recorded that temperature, to cool the inclusion from that point to any lower temperature. If the vapor bubble actually did not homogenize, then the vapor bubble will start growing in size, which we will be able to observe from the very same temperature at which we have stopped heating and we are decreasing the temperature. We will see that the vapor bubble is actually growing in size from some corner of the inclusion, and so then we know that the vapor bubble actually did not homogenize. We wrongly recorded the temperature of homogenization. So, then we have to again heat it and go a little bit higher temperature than the temperature to which we reached before, and by this kind of a process of cycling, it would be possible to exactly record the temperature of homogenization. Now, talking about a situation where there is no visibility problem, the clarity of the inclusion is very good, and we see that we have recorded the temperature of homogenization accurately by the disappearance of the vapor. And from that point, if we decrease the temperature, the vapor bubble will not instantaneously reappear, rather by decreasing the temperature to a few tens of degrees from the temperature of homogenization, the vapor bubble will suddenly pop up in a considerable size from any of the any corner of the. For example, if this has been the homogeneous inclusion, then on decreasing the temperature, the vapor bubble will just reappear just pop up, not exactly reappear, but just pop up, means suddenly make its appearance from any corner of this particular inclusion. Then we are assured that yes, we reached the temperature of homogenization. So, that is why the replicate measurements and with controlled heating rate, we would be in a position to reproduce the temperature of homogenization by plus minus 1 degree Celsius. If we have not taken enough care in our heating rate, and also during the time of a homogenization experiment, we also need to continuously focus on the bubble which is making very vigorous pseudo Brownian movement, so that we could record the temperature. If we go to temperature into the heating rate of even 0.5 degrees centigrade per minute or so, there is no it will be always easy to reproduce the temperature of homogenization by plus minus 1 degree Celsius. And this situation where, as we discussed before, this is a liquid plus vapor to vapor, and here also the temperature at which the vapor completely fills the cavity, also the similar principle can be applied. If we have not reached the temperature of homogenization, on decreasing the temperature we can still see the reappearance of the liquid instantaneously just by decreasing the temperature. But if we have attained homogenization, then the liquid again is going to suddenly reappear at a much lower temperature compared to what was recorded as the temperature of homogenization. Now, other than these two, we say, is there any other mode of homogenization? That is, of course, that is there. If you remember the phase diagram of urinary water, this is the critical point, and we discussed that actually a fluid could have been. So, if this is the critical isochore corresponding to some 0.35 grams per cc. So, if the inclusion the fluid when the mineral was growing was from the supercritical region, then let us say the inclusion was trapped somewhere here at this point, and the fluid evolved, or after the entrapment it evolved on the critical isochore, then the vapor bubble would have formed at the point corresponding to the critical temperature. We know that if it is pure water, it is 374 degrees Celsius. If it contains sodium chloride of variable weight percent, then the critical temperature will be higher. So, what will happen here is that we can think of an inclusion in which, suppose it is being heated up, it is heated, and the temperature and the vapor bubble has just been reduced in its size from an original larger size. It has just been reduced to size, and this temperature is close to the critical temperature. Then suddenly during the homogenization would not be by further reduction of the size of the bubble. The vapor bubble will not reduce in its size any further, but simply will disappear by fading of the meniscus. Means I can just say that it will just fade, the meniscus will fade there and it will become homogeneous. So, that will be the homogenization, which will be the critical homogenization. So, that will be known as, so where the homogenization will be observable by fading of the meniscus. So, if this is the liquid vapor interface, the meniscus here, as we see here, in this case or in this case. So, instead of, so when we reach a temperature, instead of any further decrease of the size of the vapor bubble, it will just fade there, it will disappear. So, that is actually is the critical homogenization. So, these are the three possible situations in which an aqueous biphase inclusion will respond to heating. We will consider heterogeneous the situation in which the entrapment is likely to be inhomogeneous later on. We will not discuss them now. Okay. So, now the situation is that we sometimes need, or the parameter which I was telling is the degree of fill, the vapor by vapor plus liquid ratio. We can see this equation here. This actually came from a very simple mass balance consideration, because if we are having an inclusion here and this is the liquid, this is the vapor, if we consider the total mass of this particular inclusion, the total mass will be mass of the liquid and plus the mass of the vapor. So, if we only know in terms of density. So, when if we consider a situation where the the vapor bubble has homogenized for L plus V to L. So, what we do exactly that we calculate the density of the fluid at the temperature of homogenization. So, we designate it as rho Th, that is the density at temperature of homogenization, and that is what exactly we calculate and we report, and we characterize the volumetric property of the inclusion fluid in this particular parameter. So, now this is a situation corresponding to 25 degrees Celsius or our room temperature, and the inclusion becoming fully homogeneous is corresponding to the temperature of homogenization. The density of the inclusion is actually when it is in one phase. So, now how we know that actually what has been the vapor by vapor plus liquid ratio at room temperature, what we call as the degree of fill. So, by simple mass balance consideration, so if I say that okay, the mass of the vapor is volume into density, and here also the mass of liquid is volume into density, here also the complete inclusion cavity also total mass. So, by doing this by calculating the masses or putting the expressions for mass of the individual the component liquid and the phase like liquid, vapor and the total, this equation was proposed by one of the pioneers worker of fluid inclusion, Robert J. Bodner of Virginia Polytechnic, United States. So, this was the expression which we can now what we could do here is that the density of the vapor phase, if we neglect, because we know that at room temperature the density of this vapor would be very negligible. So, if we neglect the density by which we will not be introducing any great error. So, if we neglect the density of the vapor phase, like the expression which you see here, that the density of the vapor at 25 degrees centigrade. So, this can be so here there is a bracket missing. Okay. So, this is the volume of the vapor into a factor which is density of the vapor at 25 degrees centigrade minus the density of liquid at 25 degrees centigrade divided by the density of the inclusion at homogenization temperature, the place of rho it has been put as d, and the density of the liquid at 25 degrees centigrade temperature. As we know, the density of the liquid at 25 degrees centigrade will be higher than the density at temperature of homogenization, where the temperature is higher, because the density is by virtue of the temperature and the salinity. So, salinity remaining fixed, the density will be lower as we increase the temperature. So, the rho Th will always be less than the rho measured at 25 degrees centigrade. So, by neglecting the density of the vapor, this equation could be reduced to a form like this, that V vapor by V inclusion is simply the density of the liquid at 25 degrees centigrade minus the density of the inclusion at temperature of homogenization divided by the density of the liquid at 25 degrees centigrade. We can get the value of the vapor by vapor plus liquid. So, that is why I initially suggested that there is absolutely no point in going for any visual estimation of the degree of fill or the V by V plus L liquid, because we can always calculate this particular parameter depending on whatever we might need to. Okay. So, as we know that from the freezing studies, we have approximated the composition of the liquid in terms of the weight percent NaCl equivalent, means the depression in freezing point that would be caused if this inclusion contained the entire dissolved solid as NaCl, and also with the assumption that the anion, dominant anion which is responsible for depression of the freezing point is chloride, and the density that is expressed as a density at homogenization is rho Th, as I just mentioned. Here it is the density is the Th. This is for any fluid inclusion work. and the calculation of density of the homogeneous fluid is essential. This parameter has to be estimated. How this parameter can be, and we know that this parameter rho Th is a function of both temperature and composition x. So, composition is in terms of weight percent NaCl at corresponding to liquid vapor equilibrium. There has been, so as I told, that this particular system has been extensively studied, volumetric measurements have been done experimentally, and those have given enough scope for empirical treatment or empirical establishment of empirical relationship of density as a function of temperature and weight percent NaCl both. So, the one which we widely used is again the one which is proposed by Wardner in 1983, quite some time back. And if you see this equation, that it contains terms where the temperature is A is temperature may be divided by 100 and B is the salinity in terms of weight percent NaCl, and one can always take as a variable when doing the empirical fitting of the parameter. So, there experimentally determined volumetric measurements where the density is known, and that is going to be regressed empirically fitted with salinity and temperature. So, in that case conveniently one can possibly put this temperature will be always in form of 100. So, it is better to normalize them by dividing to 100, and salinity will be only in the value of 10. So, by 10, and the A parameter is temperature by 100 and B is salinity by 10, and this equation where it goes to the power of in 7th power of 7 in the salinity or power of 8 in temperature, that we could see here. So, anyway, this is a regress from limited volumetric data. This is applicable only within the range of temperature and composition of experimental data. These of course, depending on what is the range of temperature and composition in which the experiments were done, and the applicability of the equation will be only be within that range. There has been many other forms, I mean many other equations which also proposed. So, this is and also the author cautioned that this should not be utilized, should not be used if there is a critical homogenization. So, that means we have to use a different set of equation for calculating the density at temperature of if the homogenization happens to be critical homogenization, and we know the weight percent NaCl and we know what is the critical. So, such equations are also there to calculate the critical temperature for water containing variable concentration of sodium chloride. And when the author proposed this equation, he reported that it is the uncertainty in density calculation could be of the order of 0.00469, it is 0.004, and we generally report density up to the third place of decimal. So, this also to be kept in mind, and this density parameter we have to measure, we have to report, because when we measure this inclusion in large number, we have to see what kind of density variations we are observing, and accordingly we make our interpretation for the fluid in terms of its origin or the way it has evolved. The other important parameter or other important exercise that a fluid inclusionist has to do from the microthermometric data is to construct an isochore, and the isochore is essentially the isochore means we understand this the dp by dt slope, like the one, this is our inclusion, this is the boiling curve, and this line, it is a straight line at least in case of the sodium chloride water system, where we say that the pressure we presume, and it is also quite clear that in such kind of binaries like sodium chloride and water, the pressure of the fluid will be a linear function of temperature, and that is the reason why, and give at a fixed weight percent of NaCl, the pressure will be a direct linear function of temperature. So, that is the reason why we say the dp by dt has to be constant. So, we need to calculate this dp by dt. and as has been shown here, the source that has been taken, the Bodnar-Bedick 1994, the dP by dt slope has been empirically fitted as a function of salinity and temperature of homogenization. Th is temperature of homogenization. It is a second degree equation in Th and linear in salinity, with the A, B and C parameters which are worked out the way it has been shown here. The As, Bs into Th and Cs into Th square. So, here you could see that the parameters are again fitted as a function of salinity, which goes to the fourth order polynomial in salinity. So, these coefficients, so this only this the very purpose of discussing this and bringing this kind of procedure to your knowledge is that to make you realize that the results of microthermometry need to be there is a good amount of exercise at hand to, after the microthermometric experiments are done and the temperature recorded at different phase changes, like the temperature of melting of ice, temperature of melting of hydrohalite, temperature of melting temperature of homogenization and so on. So, these have to be used to make some rigorous and extensive calculations, and sometimes it may not be, and a basic understanding of them is very essential, and it may not be possible to do by hand, and that is the reason why fluid inclusionists have to take help of a computer, write computer codes or use available computer programs or softwares to calculate these parameters, the isocores. So, one need to have minimum 2 points, 1 point corresponding to the temperature of homogenization here, which is Th, and at least another point or 1 or 2 point anywhere in space to construct the isocore. So, here, so if, the dP by dt slope is given here, which can be calculated. So, once the slope is known, then the pressure at any particular temperature can be known by just integrating it, and so this will be the slope, which is this parameter, entire parameter which is worked out, which is the slope, with the help of the salinity and the temperature of homogenization. So, the pressure at any point will be the slope multiplied by the temperature at which we want to calculate it minus the temperature of homogenization plus the vapor pressure. As you could see from here, the integration would be a definite integral. So, where the P will be equal to, that means it will be P minus P vapor. So, P vapor is the vapor pressure of that particular liquid of this known concentration of sodium chloride, and which can be put in this kind of equation. So, if we calculate, so the pressure at the temperature of homogenization is the vapor pressure here. The temperature at, sorry, the pressure at Th is the vapor pressure, because that corresponds to the liquid vapor equilibrium coexistence. This vapor pressure can be calculated from standard formulation, and so knowing the vapor pressure at any at the temperature of homogenization, and then the required temperature. Suppose, for example, we want to, if the situation is that the temperature of homogenization has occurred at temperature of say 200 degrees centigrade, and we need to construct the isocore. So, you will need to calculate the pressure, maybe I will calculate it at 300 degrees centigrade and maybe at 400 degrees centigrade, and we will join the 2 points with the vapor pressure value to get the pressure at those corresponding points and construct the isocore. So, that actually is an exercise which can be done for a particular or a single inclusion, and if required it can be done for many such inclusions depending on what exactly one wants to do with the fluid inclusion data. Well, so we here when we are discussing about the thermal response, heating, freezing, heating study, heating to the aqueous biphase inclusions, we should remain aware about certain problems. So, that is what I have written here, that be aware of this, because as we know that when we have reached the temperature of homogenization, if we further heat the inclusion, it is going to follow the isochore. So, if the isochore is a steep isochore, that means it actually the pressure that is exerted by the fluid on the wall of the inclusion goes on increasing. As you have discussed, as you have mentioned several times, that quartz is a ubiquitous host. Quartz is a very suitable host to study fluid inclusions, because it withstands the internal pressure because of absence of cleavage. One such reason could be cited, that because there is no cleavage, it is a solid 3-dimensional network of the silicate SiO4 tetrahedron on the linkage, and so that is why it possibly would be able to withstand higher pressure. But then there is always a limit to what a host quartz will be able to withstand. There could be some such situation that the host quartz already would be in a state of lower strength because of some reason, or there could be fractures, or there could be micro fractures around the inclusion and so on. So, what will happen is that suppose this inclusion is the one which is not in, we are doing a heating experiment for another inclusion which is homogenizing at a higher temperature. In this time, this particular inclusion has already homogenized and has been heated. So, any temperature on the isochore or beyond the temperature of homogenization, we can say it is overheated, and as the isochore that is followed by this particular inclusion is steep. So, there is much increase in pressure with small increment in temperature. So, the pressure which is exerted by the wall will exceed the strength or the yield strength or the pressure that the host crystal could withstand, and that is the reason why what happens, some phenomena which takes place, which is we call as the inclusion decrepitates, or decrepitation is a total loss of the content. It does not decrepitate, but it actually gets leaked, means the inclusion was because the coefficient of thermal expansion is quite high, and we are conducting the experiment at atmospheric pressure, normal pressure condition. So, the pressure, there will be always a differential pressure that is being exerted on the wall of the inclusion, and that will exceed the yield strength. So, what happens here is exactly what happens is the content of the inclusion will be getting leaked, a small portion of the content of the inclusion will get leaked and again gets sealed within the very periphery or the very nearby to the host, to the parent inclusion. So, again when we decrease the temperature, when we are doing the cycling of the temperature increase and lowering and increase of the temperature, we will find that the original inclusion, as you could compare here, the size of the vapor bubble is become higher here, because of the fact that the content has been leaked, and we will see a satellite inclusion which is very much nearby. And we might sometimes what it might happen, that instead of just the leakage to form a single satellite inclusion, it might also form a number of such small satellite inclusions around the parent inclusion, which you can see. So, these are the ones it is advised. Of course, we will be getting into this topic of how the inclusions are affected when they are subjected to conditions which are different from their isochoric path of evolution. Details of it we will look at it, but for the time being, during routine microthermometry, it is always expected that we should avoid taking measurements on such inclusions, because of the fact that we may. So, what will happen is that why we will avoid, the reason is very simple, that if we take a temperature of homogenization for this inclusion which has resulted, which is earlier leaked, then the temperature of homogenization that I will be achieving at the second stage will be higher than what was the actual original temperature of homogenization. So, many a times when the some abnormally high values of temperature of homogenization are observed, it is sometimes suspected that whether we are taking measurement of the homogenization experiment we are doing on an inclusion which possibly might have been earlier leaked. So, if we look at it carefully, then presence of such kind of satellite inclusions will always give us a very clear cut indication that it was leaked earlier. Such kind of leakage of the inclusion also could have happened in nature itself, when the rock was not exposed to the surface, but was subjected to some perturbation after the inclusions were entrapped in the host mineral, which is very expected, as we will be discussing such cases later. So, in such kind of situation, if somehow we miss this clue, still take the temperature of homogenization of this inclusion which was earlier leaked, the only problem that we will be facing is that we will get a higher temperature of homogenization, means the temperature of homogenization which would be in a way incorrect. There are many such. So, now here in this particular context, the inclusions which are like pure carbonic inclusion, where the dP by dt slope will be much shallow, and even if considering the fact that a inclusion which is less dense, if that inclusion is overheated, the chances of that particular inclusion leaking will be less compared to an inclusion where the density is high, because there the dP by dt slope is high. And then the other aspect is that it is also suggested from very elaborate study conducted by many of the experts, that the chances of leakage of these inclusions will always be higher for inclusions which are larger. Means the inclusions which are of the order of 30, 40, 50 microns in their maximum dimension, if those inclusions are overheated, the chance, because the surface area is more and the pressure that is exerted on the inclusion wall, it might be able to, it might not be able to withstand, whereas the smaller inclusions will always escape, or the chances of leakage of inclusions which are smaller than a particular value will be always, survival of those inclusions are higher. So, but on the contrary, there are situations that we always advise that because of certain reasons which we will be discussing later, that it is always the reliability of the microthermometric experiment is also better if the inclusion is larger than a certain value. Say for example, generally we advise that do not subject an inclusion to microthermometric experiment if it is less than 5 micron in its maximum dimension. We will come back to the reason why. So, for the timing, to conclude, there could be many aspects on which there will be lots of curiosities, lots of questions regarding the microthermometric experiments and the behavior of the inclusions, response of these inclusions to heating freezing cycles, but within this time frame these are some of the practical tips that could be offered, and we will continue discussing on this in the next class. Thank you.